Hi, what I'm going to do in this video is quickly describe the notion of the Isom Presheaf associated to two objects in a fibered category. So suppose you have such a thing, so f down to c via a functor p is a fibered category over c. Then if we choose some object in c, and if we choose, let's say, C1 and C2 objects in F that lie over our object X, then, so this is to say that P of each of these guys is my object X, then we can define a new fibered category that we're going to call the Isom fibered category of isomorphisms between C1 and C2. This is going to be a category fibered not over C, but over the comma category over X. And so how is this going to work? Given, so what are the objects of this category? Well, the objects are described by a bunch of data, but a more intuitive diagram. Let's say G, comma G1, comma G2, comma C, where G is going to be some map in the some object in the comma category, some object mapping to X, and the GIs are going to be Cartesian arrows above G, so we have something like the following, with whose target is going to be the CIs. So down here we have G mapping to X. Above X we have a couple of objects. Let's say we have the object C1 and the object C2. The idea is that these two things might not be isomorphic, but after taking some Cartesian arrows, so this is going to be a Cartesian arrow, say G1, which pulls C back to, let's say, C1 prime, and we have a Cartesian arrow G2, which is going to pull C2 back to some guy C2 prime. These things are going to be, again, lying over now U. So we have a couple of Cartesian arrows, and then psi is going to be an isomorphism between the pullback objects. So the idea is that Isom is going to be a fibered category that's going to keep in mind not necessarily the isomorphisms between the literal objects C1 and C2 as they were first described, but just isoms between pullbacks of those, so restrictions, if you will, of these families, if you're imagining these things as families, over various open sets. Okay, so these are the objects. What are the morphisms? So if I have a couple of diagrams like this, well, a morphism is going to be a way, making a kind of a large commutative, not just commutative, but really a Cartesian diagram. So let's say, so we're going to say what is a phi1, phi2 is going to be a morphism between the data of, let's say, maybe we'll call it, how did I label these things above? Let's say H, H1, H2, I need another letter, let's just call it psi prime, because I'm not very creative right now, to G, G1, G2, psi. It's going to be a picture that looks something like this. So on the one hand, we have our objects, our original objects, psi1, or C1 and C2, lying over my X. I have some U via G. I have mapping, so I have my Cartesian arrows. So let's say I have a Cartesian arrow over here, That's going to be my C2 prime, just as before. I have my C1 prime. These are objects that live over U, just as the diagram up here indicates, and I have some isomorphism psi between them. So this, if we are keeping track of things, are my G's, which are encoding this data right here. So now I want to map from a new diagram with some H's to this diagram with some G's. So let me scroll this up, and just to keep things straight, let's say this is that's the data which describes my G, and now I'm going to describe an H. So this is going to be given by, let's say, some C1 double prime, C2 double prime. These are going to be some objects lying over some different base V. I'm going to have phi be some morphism from V to U, but V is also going to be, V together with the C1 and C2 is going to be this object described by these H's. So this is going to be some map H. I have some Cartesian arrows which take these guys over here. And then I have an isomorphism between them, which is my psi prime. So now these guys are, this is going to be the data, just to remember, that describes that guy there. Okay. And so now a morphism between these two diagrams, from the purple to the blue, and this psi prime is also part of the data of the purple, is going to be a Cartesian arrows phi1, phi2 over phi, such that the diagram above commutes. So I'm going to need an arrow between the size, phi1, arrows between the size, phi2, which lie over my phi, such that the diagram commutes. So, call these things the yellow map. So this is this is that map right there. To make it clear what's going on, let's isolate this part of the diagram and notice that if we have a commutative diagram downstairs in the category C, and objects in F lying above them, such that these arrows lying above these ones are Cartesian, like we have in our definition, then one of the axioms of the fibered category is exactly that there should be a unique Cartesian arrow between these two objects. We know that these arrows, phi1 and phi2, since they're Cartesian, are unique. That's one of the axioms of the fibered category, that there are these unique ways to fill in these Cartesian arrows lying above these commutative triangles. So what we find is that, so first off, I have to say, this is a fibered category, right? So we've defined just the objects and the morphisms. We need one more piece of data, which is how the thing actually maps down to C. And the deal is that an object of this shape, G1, G2, psi, is going to map down to the object U. In other words, the thing that lies above the source of these arrows, Gi, is going to map down to U. The data phi1, phi2, the morphism of this sort, is going to map down to the morphism just given by phi, which, if you recall, is the map on the bottom in the comma category itself. And what we find is that lying over a given arrow down here, there's going to be a unique guy upstairs. So arrows upstairs, lying above arrows in C are unique in this particular fibered category, Isom. Well, in particular, that says that if I look at any of these fibril categories of the form Isom so C1, C2, Isom lying over some particular object, U to X. So what does that mean? This is a category that, these are the categories that lie above a particular object, and I'm looking at morphisms that are coming from the identity morphism downstairs. But lifts are unique, so there's only one thing lying over the identity morphism. So that says that, so in here, all morphisms are identity morphisms. And now we're basically done. Remember that an equivalence relation is a category in which all the morphism sets are either empty or a single object, and all the morphisms are isomorphisms. This is exactly what we have in our situation. We also showed at some point, which is not hard to do, that that such a category, which we're calling an equivalence relation again, you can check if a category is such a thing, if it's simply a groupoid such that the automorphisms of every object are only the identity. And notice that's exactly what we've shown here. So what we now have is a category fibered in equivalence relations. And next, it's not too bad to see that if you have a category which is an equivalence relation, if you move to the skeletal category of that equivalence relation, that is to say, you choose an isomorphism class of object for each object and you forget all the rest, then such a category is equivalent to, there's a natural functor that for any of these categories that takes it to a category whose morphisms are only the identities, which we think of as a set. So there's a natural functor from any, called pi naught, from any equivalence relation to a set. And by doing this to our Isom sheaf, we take our category fibered in equivalence relations, and from it we get a category fibered in sets, and this is a pre-sheaf, a functor, and that's the Isom Presheaf.